Good morning, students. In today's lecture, we will discuss about the unit vector along the tangent to a given curve, arc length, and related examples. So, first of all, let us derive an expression for the unit vector along the tangent to a given curve. Let us take a curve denoted by C. P and Q, these are 2 points on this curve. O is origin. Let us take the position vector of point P, which is denoted by the vector OP. This is vector R. And the position vector of point Q, this is the vector OQ. And this is R plus delta R. Now, in this triangle OPQ, let us apply the triangle law of vectors addition. So, by using triangle of vectors addition, in this triangle, we can write vector OQ is equal to vector OP plus vector PQ. Putting the values, vector OQ, this is R plus delta R. Vector OP, this is vector R. So from here, we can find the value of vector PQ. So vector PQ will be vector OQ minus vector OP. So that will become delta R. Now, let us take A is some fixed point on this curve C, and let the arc length AP, that is S, and the arc length AQ, that is S plus delta S, and therefore the arc length PQ, that will become S plus delta S minus S, that will become delta S. Now, let us find the unit vector along the chord PQ. By definition of unit vector, this is given by vector divided by its magnitude. Here the vector is vector PQ. So, the unit vector along the chord PQ, that will be vector PQ divided by its magnitude. Now, multiplying and dividing by delta S, and also the vector PQ, that is the vector delta R, and its magnitude we have denoted by delta R magnitude. Now, in the figure we can see that as the point Q will approach to the point P, this chord PQ, that will become a tangent at the point P. So, taking limits as Q approaches to P, in this expression we will get unit vector along the tangent at the point P. So, taking limits as Q approaches to P. Now, because the arc PQ, that is delta S, as Q approaches to P, delta S will approach to 0. Therefore, we can find the unit vector along the tangent at the point P as limit delta S approaches to 0, delta R by delta S, because this expression, that will become 1, because as Q approaches to P, arc PQ and chord PQ, they becomes same. So from here, the unit vector along the tangent at the point P, that is dr by ds, and it is generally denoted by the vector t cap, and the derivative with respect to s of the vector r we denote by r dash. So this is the expression for the unit vector along the tangent at the point P. This is the expression for the unit vector in terms of perimeter S, where S is the arc length. To find the expression for unit vector in terms of parameter T. Now by definition, because the unit vector T cap is dr by ds, this can further be written as dr by dt upon ds by dt. From here, we can find dr by dt. This will become t cap into ds by dt. Taking magnitude on both sides, the magnitude of dr by dt is equal to magnitude of the unit tangent vector t cap into the magnitude of ds by dt. Now because t cap is a unit vector, so its magnitude will be 1. So the magnitude of dr by dt becomes ds by dt. Now putting the value in the formula for t cap, we get t cap is equal to dr by dt divided by its magnitude. So this gives us the formula for the unit tangent vector at a point to the given curve. By using this formula, we can find an expression for arc length of a given curve. You will continue this article up to this step, and after that we will find the formula for the arc length. Now from here, because dr by dt magnitude is ds by dt, so from here ds will become the magnitude of vector r dot into dt. If we are to find the arc length between the points t naught and t, then it can be obtained by integrating both sides between the limits t naught to t. So if we integrate both sides between the limits t naught to t, this gives us integral t naught to t ds is equal to integral t naught to t r dot magnitude dt. Now if we consider the vector r given by xi plus yj plus zk, differentiating both sides with respect to parameter t, derivative with respect to t we have denoted by dot. So this will become r dot. Derivative of x with respect to t is x dot. Derivative of y with respect to t is y dot. Derivative of z with respect to t is z dot. So r dot becomes x dot I plus y dot j plus z dot k. Taking magnitude of this vector, by definition, magnitude of this vector is given by square root of x dot square plus y dot square plus z dot square. Now let us substitute the value of magnitude of r dot here. So we get the arc length s is equal to integral t naught to t square root of x dot square plus y dot square plus z dot square dt. So this gives us the formula for the length of arc of the given curve. Next is the definition. What is normal form of a curve? The equation of the curve in terms of arc length, that is normal form of the curve, and we have denoted the arc length by s. So we can see that normal form of the curve is the equation of the curve in terms of parameter s. Now we will discuss some examples related to unit tangent vector and length of the arc of given curve. So our first example is, find the length of circular helix given by vector r is equal to a cos t I plus a sin t j plus c t k. Here t belongs to the open interval minus infinity to infinity. We are to find length of the circular helix from the point a00 to the point having the coordinates a, 0 and 2 pi c. And also we are to find the equation of the curve in terms of parameter s. It means normal form of the curve. So in order to find the arc length, we require the magnitude of the vector r dot. Now because the vector r is a cos t I plus a sin t j plus c t k. To find r dot, differentiating both sides with respect to the parameter t, we get r dot is equal to minus a sin t I plus a cos t j plus c k. Now taking the magnitude of this vector, by definition of magnitude of a vector, this is given by square root of minus a sin t whole square plus a cos t whole square plus c square. So the magnitude of vector r dot is square root of a square plus c square. Now we are to find the length of circular helix from the point having the coordinates a0, 0 to the point a0, 2 pi c. Now because the value of z is ct, and from here we can see that z varies from 0 to 2 pi c and z is ct. So ct varies from 0 to 2 pi c. Therefore the limits for the parameter t are 0 to 2 pi. Now by the formula for arc length, the length of circular helix from the point having the coordinates a0, 0 to the point a0 and 2 pi c is given by integral 0 to 2 pi the magnitude of vector r dot dt. Substituting the value of magnitude of r dot from here. Now because under root a square plus c square is constant, so integration of 1 with respect to t, that will be t. Putting the limits, we get length of circular helix, which is given by 2 pi into square root of a square plus c square. In the second part, we are to find the normal form of the curve. To find the normal form of the curve, we are to eliminate t from the given equation of the curve. So let us find the value of t by using the formula for length of the arc between t is equal to 0 to any point t. Now by using the formula for arc length, it is given by integral 0 to t magnitude of vector r dot dt. Putting the value of magnitude of r dot here. Now because this term is constant, so the arc length s becomes under root a square plus c square into t. From here t is s upon under root a square plus c square. Now you can substitute the value of t in the given equation of the curve. So we get the required normal form of the curve. Now our next example is find the length of the curve given as the intersection of the surfaces x square upon a square minus y square upon b square is equal to 1 and x is equal to a hyperbolic cos z upon a from the points having the coordinates a0, 0 to the point having the coordinates x, y, z. Now because the curve is the intersection of these two surfaces, let us write the parametric equations for this curve. Now because we can see that x is equal to a hyperbolic cos t and y is equal to b hyperbolic sin t satisfies this equation, because hyperbolic cos square t minus hyperbolic sin square t is 1. So we can take x is equal to a hyperbolic cos t and y is equal to b hyperbolic sin t. Let us take z upon a is equal to t. So z will become at. So these are the parametric equations of the given curve. Now because we are to find length of the curve, so let us find the derivative of vector r with respect to parameter t. Now by definition, the position vector of any point on the curve is given by vector r is equal to xi plus yj plus zk. Putting the values of x, y and z here, we get vector r is equal to a hyperbolic cos t I plus b hyperbolic sin t j plus at k. Now differentiating both sides with respect to parameter t. The derivative of hyperbolic cos t, that is hyperbolic sin t. Derivative of hyperbolic sin t is hyperbolic cos t. Derivative of at is a. So we have obtained r dot. Now taking magnitude of this vector, So by definition of magnitude of vector, this is given by square root of a hyperbolic sin t whole square plus b hyperbolic cos t whole square plus a square. Simplifying this expression, we get magnitude of r dot, which is under root a square plus b square into hyperbolic cos t. Now we are to find the length of the curve from the point a00 to the point xyz. Let us take the limits of parameter t from t is equal to 0 to any point t. So by the formula for arc length, the length of the curve is given by s is equal to integral 0 to t magnitude of vector r dot dt. Magnitude of vector r dot is under root x dot square plus y dot square plus z dot square. Now putting the value of this expression from here, we get s is equal to integral 0 to t under root a square plus b square into hyperbolic cos t dt. Now this term is constant and integration of hyperbolic cos t is hyperbolic sin t. Substituting the limits here, we get s is equal to under root a square plus b square into hyperbolic sin t. Now because y is b into hyperbolic sin t, so from here hyperbolic sin t will become y upon b. Putting the value here, s is equal to under root a square plus b square into y upon b. So this is the length of the curve. Now next we discuss an example based on unit tangent vectors. Find the unit tangent vector t cap. Find the unit tangent vector t cap and the direction cosines of the tangent at any point to the circular helix. The parametric equations of circular helix are x is equal to a cos t, y is equal to a sin t, z is equal to bt. To find the unit tangent vector t cap, by definition, unit tangent vector is given by the vector dr by dt divided by its magnitude. So first of all, let us find dr by dt. Now by definition, vector r is given by xi plus yj plus zk. Putting the values of x, y and z, the vector r becomes a cos t I plus a sin t j plus bt k. Differentiating both sides with respect to t, this will become dr by dt. Here the derivative of a cos t will be minus a sin t. Derivative of a sin t is a cos t. Derivative of bt is b. So the vector dr by dt becomes minus a sin t I plus a cos t j plus b k. Now by definition of unit tangent vector, this is given by dr by dt divided by its magnitude. Putting the values of both dr by dt and its magnitude, denominator that will become under root a square plus b square. In the numerator we have minus a sin t I plus a cos t j plus b k. So this gives us the unit tangent vector at the point. Now to find the direction cosines of the tangent at any point to the circular helix. Direction cosines are the coefficients of I, j and k in the unit vector t cap. So these three, minus a sin t upon under root a square plus b square, a cos t upon under root a square plus b square, b upon under root a square plus b square. These are the direction cosines of the tangent at any point to the given circular helix. So this completes the topic unit tangent vector and arc length to a given curve.